Hi everyone, this is Ichitaro Yamazaki from Sandia National Lab, and today I will talk about our paper, Performance Portable Supernode-based Sparse Triangular Solver for Manycore Architecture, and this is a joint work with Siva Rajamanikam and Nathan Ellingwood, also from Sandia. Right. So first, I'd like to give some background and motivation of this talk. So as you may know, Sparse Triangular Solver is a quite important kernel in many applications, but at the same time, it is still a challenge to parallelize the kernel, especially for a many-core architecture like a GPUs. And this is because the sparsity structure of the triangular matrix often limit the parallelism available for the solver to exploit. So for this paper, instead of focusing on the triangular matrix with the general sparsity patterns, we decided to focus on a particular case where the triangular matrix comes from the local sparse direct factorization. So this means that on distributed memory computers, each of the MPI processes compute its own local factorization and apply its local sparse triangular solve independently. And we decided to focus on this particular case because quite a few applications use this approach. So for example, one particular application that we looked at in this paper is called Sierra SD, that uses a domain decomposition-based linear solver, and each of the processes applies thousands of the local triangular solve for each local factorization. So any improvement in the sparse triangular solve performance can have a direct impact to the simulation time. And to improve the performance of the solver for this particular case, in this talk, we will look at these two algorithmic variants, which are listed at the end of the slide. So to implement the parallel sparse triangular solve, a standard approach uses the level set scheduling. So for a dense triangular solve, we have to compute each of the solution element sequentially through either backward or forward substitutions. But for a sparse triangular solve, because of the sparsity of the matrix, we often have multiple solution elements which can be computed in parallel at each step. So in the level set scheduling scheme, we first find these set of independent solution elements which can be computed in parallel at each step. And then during the numerical solve, we compute these elements in parallel by level. So for examples, this top graph shows the task dependency graph of the triangular matrix shown on the bottom of this slide. And we often see this type of binary tree structure when we apply the nested dissection ordering to the matrix before the factorization. And with the level set scheduling, we compute the solution element corresponding to the leaf of the graph from the bottom of the graph to the top. So we can obtain a good parallel performance when we have a short tree with lots of leaves at each level. So even with this level set scheduling, the sparsity of the triangular matrix often limits the available parallelisms. So in this paper, we looked at exploiting the block structure of the triangular matrix coming from the sparse direct factorization, where the column with the similar sparsity structures are merged to form a single block column. So instead of scheduling to compute each of the solution elements, we designed the level set scheduling to compute the blocks of the solution at a time. So for example, in this task dependency graph of the sparse triangular solve, each node becomes a block instead of a solution element. So this allows us to reduce the number of levels in the level set scheduling, and also allow us to use a so-called batched kernel to exploit the hierarchical parallelism, where we handle all of these leaf supernodes in parallel, but at the same time, we use the threaded kernels on each of the blocks. So this block-based scheduling often improves the performance, but we still need to call this a dense triangular solve on each of the diagonal block, and this is a fundamentally sequential algorithm. So to remove this potential serial bottleneck, we can invert these diagonal blocks so that we can apply this inverse of the diagonal blocks using a dense matrix vector multiply or GEMBs. And we can further improve the performance by applying this inverse of the diagonal blocks to the corresponding off-diagonal blocks. And this allows us to merge two GEMBs to compute the solution and to update right-hand side into a single GEMB course. And this often improves the performance because it provides more parallel computations for each of the GEMB kernels. And this is a particular application of the partitioned inverse method proposed by Alberto, Posen, and Schreinberg in 1993, where we compute the partitions based on the level sets of the supernodal blocks. So with this approach, we have transformed this sparse triangular solve into a sequence of sparse matrix vector multiplies. And instead of batched GEMBs, we can also call sparse matrix vector kernels at each step. And this routes some of the information about the block structure of the matrix, but it avoids the operation with explicit zeros. And we also have often optimized version of the sparse matrix vector kernels on a particular Manycore architecture, and this may lead to performance gains. So we implemented our solver using Cocos and Cocos kernels, and we have some details about our implementation in the papers, but basically this allows us to develop the solver which is portable to different Manycore architecture using a single code base. And for the data structure, our solver uses the standard CSR or CSC sparse matrix format. And for our experiment in this paper, we just use SuperLUs, but these solvers are also interfaced to Choromod. And on our GPUs, we will be comparing the performance of our solver with the sparse triangular solve from SuiteSparse. So first, this graph shows the sizes of the supernodal blocks for one of the matrices from Sierra SD simulations. And we see these lots of small blocks in the beginning of the triangular solve, and at the end of the solve, we start to see a fewer but larger blocks that we need to execute. And the graph on the right also shows the same block sizes, but now we have merged the block column with the same sparsity patterns, and this often improves the performance of the solver because it reduces the number of the levels and also increase the computational intensity at each level of the scheduling. So finally, we show the performance of a solver on GPUs, and the left graph shows the speed up over the SuiteSparse using different solver options. And our default options uses the standard device level GPU kernel, such as Kubras, on each of the blocks. And it really shows that using the team level or batched kernel is critical to get the good performance of the solvers. And this graph also shows that inverting the diagonal blocks and applying the inverse to the off-diagonal can further improve the performance. And we see the speed up of up to 8.7 over SuiteSparse for this particular matrix. And also in terms of the numerical stability for all the matrices used in this paper, we saw the same order of solution accuracies using all different solver options, including partitioned inverse. So now this slide shows the speedups over SuiteSparse for different sizes of the matrices coming from CRSDs. And we see these different speedup, but still quite significant speedup for all of the matrix sizes. And the graph on the right shows a breakdown of the solve time. And with the current implementation, this kernel launch time can be significant, taking up to 30% of the total solve time. And we also look at the performance of our solvers for matrices from SuiteSparse matrix collection. And we see these different speed up or even slowdowns of our solvers, and this is because the performance of our solver really depends on the sizes of the supernodes and the number of the levels that we can extract from the sparsity structure of the triangular matrix. So here is just a quick summary of today's talk. And we are currently working to further improve the performance and also providing interface with other packages, including incomplete reuse. And all of our solvers are available from Cocos kernels and Trilino packages. And I hope you can give it a try. Thank you.